Because we like to stick to well-proven formulas, UT Austin's Portugal Masterclasses are back. In this year's edition of the program's annual conference, over 10 thought leaders across 5 broad fields of expertise will delve into some of the trendiest topics that are shaping global research and innovation agendas. From new generation batteries to protein therapy for cancer treatment, high-performance computing, deep-sea exploration, and management of technology implementations. Almost 12 hours of pure knowledge sharing. Keep pace with what is bolstering your research area and the industry. Connect with world-class speakers from Portugal, the US, Spain, and Germany, and get their feedback. Be part of a constellation of forward-looking people who recognize the value of continuous learning to excel and advance science-based knowledge.
Hello everyone, and welcome back. It's my great pleasure to introduce our next speaker of the HPC or Advanced Computing Area Masterclass. So we were supposed to have 2 teachers today, Matteo Valero and John Davis. Matteo unfortunately could not make it, but I'm completely sure we are very well served with John. So John Davis is Director of the Laboratory of Open Computer Architecture at the Barcelona Supercomputing Center. He has published over 30 refereed conference and journal papers in computer architecture, distributed systems, and bioinformatics. He also holds over 35 issued or pending patents in the US and Europe. John holds a PhD in electrical engineering from the Stanford University and also leads several industrial research collaborations, all centered around a full open source ecosystem from software down to hardware, open source processors, and accelerators. John is the founder and chair of the RISC-V Special Interest Group on High-Performance Computing. So, John, the floor is yours, and thank you very much for coming.
Thank you. First, I'd like to thank the organizers for inviting us to talk today. It's been an exciting opportunity to share with you some of the HPC work that we're doing. This is meant to be open and collaborative, so if you have questions along the way, please don't hesitate either online or in person to ask. I'm hoping that we can have a fun conversation and really talk about some of the things we're doing at BSC and then more broadly how we view European supercomputing in general. And so this is some of the things I'm going to talk about. So as the title mentioned, we'll be talking about defining an HPC open ecosystem. And really first we need to know where we are today and then understand how that's going to evolve to get us to that point tomorrow. And we really want to leverage some of the exciting parts that open source software has shown us and what we can do in the context of open source hardware as well. And so I'll touch on those pieces. The agenda for today is basically going through these 6 topics. I'm going to talk about the history of high performance computing in general. It's not going to be a really deep dive, but it's going to give you some context in with regard to technology. For those that aren't aware of what BSC is, I'm going to give you some of the information history on BSC and the components of the lab that makes it unique. And then we're going to talk about HPC today. And then about halfway through, we'll take a little bit of a break just so everyone can take a rest, and then go into open ISAs, in particular RISC-V, and then building that open ecosystem. How do we get there? And then some concluding thoughts on what our vision is for Europe and how we can create the next evolution in high performance computing. So with that, I think hopefully that's pretty straightforward. Again, if you have questions at any point in time, please don't hesitate to ask, and I'm happy to answer them. So this may seem a little bit strange, but I did want to start off with why do we need HPC? And so we're seeing computing being fundamental to everything that we do today. And fundamentally, at that level, if we have high-performance computing, it can answer a lot of the open questions. So given climate change, given particulate matter in the air, we can do modeling of that and understand what we can do to make the world better. In particular, there's a lot of work in personalized medicine. So how can I create custom vaccines, custom drugs for individuals based on their genome, and do that in a very rapid, quick method. We can use it for industrial purposes. So thinking about aircraft, automotive, how do I simulate these systems to create better, more efficient systems? And obviously, understanding the human body in general, whether it's the brain or other systems. So that's kind of the fun part. And we're also seeing this evolution of digital twins. These are systems which are digital representations of the real thing, and we can use them to understand the systems better, to design them, those types of things. And we're seeing a lot of this in industry, whether it's airplanes, boats, what have you. This gives us a lot of capabilities, and these models require a lot of computational capabilities. So this is where we see HPC fitting in. And as I mentioned before, there is this notion of that for future medicine. So can I take you as an individual, bring you into the system, digitize your body and characteristics, genome, those components, and then understand in whatever phenomenon that's affecting you, how I can actually model that, and then create drugs or therapies specific to you. So you could run hundreds or thousands of experiments to actually find the most appropriate drug or create a custom tailored one. So this is really where it's an interesting aspect of how we can transform our quality of life and improve our existence. And so, you know, what level of simulation do we do? How can we get the right type of scenarios in the system? What are the types of modalities within medicine that we can actually use this for? And so this could be cancer, it could be other types of things. So it's a very interesting space in terms of using high computational capabilities to do that. So I'm sure you're familiar with that. We kind of talked about it in some of the earlier talks today in terms of high performance computing, or at least areas where high performance computing could impact. So let me switch gears a little bit and move into the history of high-performance computing. And one of the interesting things is, if we look at us today, you could take each of us as a high-performance supercomputer. And I say that because if you look at what various companies are doing for creating self-driving cars, if you can drive, you can do more than what a supercomputer can do today. So that's a very interesting aspect to think about, that you in some right are a supercomputer, and we all have different talents, so just keep that in mind. So if we look at this, when we think about instruments, they really accelerate our application or acquisition of knowledge. And so going back many centuries ago, how do we actually build these out and what do we use those for? And so I want to start with this kind of space in terms of thinking about that creation of knowledge and using supercomputing as that basis. Now, if we fast forward in relatively short order, we created transistors just at the end of World War II, integrated circuits about a decade later, and then in the early 70s we had the first microprocessor from Intel. And so you see this rapid evolution of technology and different technologies to support that. Now, if we start with that first computer, it's relatively small. Undergraduates today design more complicated computers than what the Intel 4004 was. But it was about 2,300 transistors, a very large technology running at 100 kilohertz. So not very fast, but it was the genesis for all the things that we do today. Now, if we fast forward to today and we look at high-performance computing, IBM creates the Power series, and it has many, many processors over the generations. We're up to the forthcoming Power 10. We've gone from 2,000 transistors to billions and billions of transistors, and that's the exciting part of this. We're seeing this rebirth of how do we think about computing, and going from a single core up to 30, 60, 100 cores in a single chip. And so we see this interesting evolution of this. Now, the challenge here with IBM and Intel and all these other processor companies is they're generally closed source. So if I have an application I'm trying to accelerate or customize, I'm limited to what I can do on the software side. I can't actually go to IBM and say, hey, can you add this feature? Or it would take many, many years to do that. And research is always striving to do that. Now, shifting gears slightly, thinking about it from the software side, we've gone through this revolution already, right? And if you think about Linux and open source, that's kind of where we are. So if we start here at the the left here, we started with closed proprietary software hardware systems. So think of the old IBM mainframes, those components. They were really expensive, rigid. They gave you a significant lock-in to the vendor. And if you wanted something added, you paid lots of money for those services. We shifted from that in the 80s and 90s to these horizontal platforms. So think of Windows, Solaris. These were operating systems where you could build software on top of them using standardized APIs. And that gave us a lot of growth. And you saw the rise of Microsoft in that context in terms of Windows and Solaris to some degree for Sun. Now, what's changed dramatically in the last 2 decades is this advent of open source hardware. So with Linux, which was derived from Europe, we've built a bunch of different services, a bunch of different communities around that, and we can see how they proliferate and grow, and that has some really good aspects. So if I build a system today, whether it's IoT or servers or high performance, Linux generally is the basis for all of these components, and then we have various business models that provide freemium, so you get the minimal functionality for free and then you pay for additional features. There's a whole bunch of different things there, but we can leverage the global community to actually build things, and so that's really what we'd like to do on the hardware side as well, is create this community for hardware that gives us that capability, and then build the entire stack. So from processors all the way up to applications and everything in between. And that's going to be a fun, long journey. But fundamentally, we get standard APIs. We have a whole bunch of things that you can customize. You can take something off the shelf and build it exactly to what your needs are, and that customization software is fantastic. Now, when we think about Linux, just to give us kind of the historical perspective, the first release was back in 1991, and so that was the start of this whole process. In the late 90s, about a decade later, there's a whole bunch of, what's the best way to describe it? I guess confusion or desires to control Linux, and a lot of major companies got involved, and that obviously caused some friction. But in the US and in Barcelona, during the late 90s, early 2000s, we saw Linux becoming the system for operating systems in supercomputers. So instead of using AIX or some of the proprietary systems from the vendors, it went to Linux, and that provided a whole new area to drive standardization and use that open system. Now, when I look at it today, as I mentioned, if I build a system today, right, whether it's Android or servers or enterprise, I'm building it with Linux. So that's an interesting place to be, and it's basically that de facto OS. And so that's kind of the fun part when we think about what we can do with OS, with the OS and with open source software. It does have its drawbacks, fragmentation, and those types of things to consider. But this is kind of the model we're looking at. How can we take the benefits of open source software and apply it to hardware, and then create an open ecosystem within the HPC space? Now, some of the fun things there, jumping onto the hardware side from a performance perspective, what I have here is I've graphed on the x-axis the time, years, and then performance on the y-axis. And what we're looking at is the best supercomputer system of that time. So this is recorded by the top 500, and then the sum of all of those together, and obviously this is the worst. So this is the space in terms of performance between what's on the list. Today we're at 415 petaflops. This is the Fugaku system at Riken. It's an ARM-based system. But way back when we looked at the first entry, right, this was in 1993, it was a thinking machine system, and it only had about 60 gigaflops. Now the funny thing about this is if I look at my laptop today, 25, 30 years later, I'm already surpassing that, right? So what I could do back in the mid-90s, I can actually surpass with my laptop today. And the same thing can be said about your phone and so forth. So it's a very interesting place just to keep that in mind, that this line shows you kind of where we are from performance, and we're able to get these step function increases in performance, and I'll talk about that a little bit more today in terms of the laws and the things that allow us to do that. Now, this is great to think about in terms of performance and how that works, but there's also some limiting factors. So when I think about the system, I have compute, I have memory, I have storage, I have networking. All those come together to produce the system that we have today. And one of the interesting aspects is they're all governed by the technology of scaling silicon wafers and silicon transistors and those components. One of the first things that we saw in terms of having problems with scaling was DRAM. And basically what ends up happening for a DRAM cell is you create a transistor that acts as a capacitor, and that capacitor is basically built into a trench. So think of almost a well, a very narrow, deep structure. And as you try to build that smaller and smaller, it gets harder and harder to actually bore down into the silicon. So think about creating, taking a small spoon and trying to dig a very narrow trench, little hole. That's what you're trying to do with silicon. And so we got to a point where we could no longer scale that structure. And so because you couldn't scale the structure, you couldn't make higher density DRAMs. And so that was an interesting aspect of scaling, and that affects the cost of DRAM and the capability to store more stuff. So as you think about our digital world, and I have some slides on that, how much data do you produce is relevant to how much DRAM you might need in the system, and how big your models are and those types of things. So that's a big challenge on that side. There's also energy and bandwidth that are limiting factors. As we see DRAM today, it actually hasn't really changed its latency or bandwidth characteristics significantly over the last 10 years or so. And so this is creating this bigger gap between the processor frequency and the memory speed. And so that's a challenge that we want to have, and this is usually called the memory wall. So how do we break through that memory wall? Now, one of the solutions here is to use new technology. So this is stacking and looking at how to repurpose this. So I can no longer get shrinks in the geometry in a 2D structure in a kind of a 2D plane, but I can take these die and I can stack them and get densities at that level. And this has led to high bandwidth memory, or HBM. So basically I'm taking die and I'm stacking them to get density, and I'm also exposing a bunch more bandwidth because I'm opening up all the banks in the different die and giving you a capability to dramatically increase the bandwidth. And so this really gives you an opportunity to use technology and transition from one problem and solve it in a new way. And I think that's one of the exciting things that we have today, looking at technology and figuring out how to make it work. Now, DRAM gives us that kind of Z vertical stacking versus XY stacking, or XY density components that we had in traditional silicon technology. And so that's nice. We still have some problems there. So when we look at that, some of the other solutions are using non-volatile memory. So Intel has Apache PAT, well, 3D XPoint is the technology name. It uses a variety of different technologies in general and non-volatile memory to create different layers of replacement memory. So it could be 3D XPoint for DRAM. It could be spin torque transfer SST memory for SRAM inside the chip. So there's a bunch of different things where we can actually use non-volatile memories to reduce some of the problems we have with power, and then we get other characteristics like persistence for free. Now, it's not a free lunch, right? If we look at all these technologies, they have some other issues. They might be asymmetric in terms of read versus write bandwidth or latency. They might have wear out characteristics, so NAND flash wears out, 3D XPoint wears out. So those are just issues that you then have to build into the system software or the system hardware to take advantage of and mitigate in whatever appropriate way that is. So fun things to think about as we think about technology and how to solve these problems. Now, how do we look at that today in terms of bandwidth, right? So what I'm showing here is the DDR5 bandwidth, and this is based on the JEDEC standard. So JEDEC basically defines how memories and systems are built and gives everyone the opportunity in that space to build to that standard. And so when HBM was started, it already had twice the bandwidth that DDR5 has. Now, when we compare DDR5, there's two different aspects of it. One is the bandwidth number, let me get that back, and the other one is the latency. So you get better bandwidth from HBM, but you don't get better latency. But as you see right now, we're in this 2E space. This is what's shipping today. So that's already 460 gigabytes per second for a single stack. And that single stack can be 4 or 8. It'll increase the number of die that go in there from HBM to HBM3, but you fundamentally have a massive amount of bandwidth really close to the die, and this is something that's actually packaged in the chip itself, right? So you have the actual die for your accelerator or chip, you have a substrate made of silicon or something else, and then you have the HBM right adjacent to that die. And so you get massive amounts of bandwidth from HBM. As you can see, we're going up to almost a terabyte for a single stack. So when we think about the bandwidth problem, we're able to dramatically increase the bandwidth that you see at the die-to-die interface and then solve some of those issues. You still have a latency problem. So we don't get everything for free. Now, that's part of the scenario. One of the other things to look at, which I think is interesting within the space, is on the networking side, right? So what I'm showing here is the time scale on the x-axis and the number of cores on the y-axis, and that's a log plot, right? So just starting back with our first thinking machines and the number of nodes, we've gone from, 1,000, tens, thousands of nodes, all the way up to hundreds of thousands of nodes in the span of this short period of time. And so you can see that the network is also critical. We've shifted from things that were maybe core focused to going to parallel systems and all the way up to these massively parallel systems like we see today with Fugaku. And I have some numbers on what those are. Now, what has changed over time is what the network topology is. How do I minimize the number of hops? How do I increase the cross-sectional bandwidth going from, say, a traditional fat tree to Dragonfly, HyperX, or some of these more advanced topologies? And they're all based on that ability to reduce latency overall, number of hops and latency per hop. And the fantastic thing here is we're seeing scenarios where you can get from the outside of the switch to the other side of the switch in, say, 100 nanoseconds, which is pretty impressive. That follows on the other technology component of this, which is the network actual interfaces. So right here I'm showing from the early 2000s to the future, I guess, what the InfiniBand link bandwidth is, right? And we have this very nice curve showing that we're going right now, we're in the kind of 400 gigabit to 800 gigabit going to terabit levels as we go from the various versions of InfiniBand. Now, the interesting thing to note was probably 20 years ago, InfiniBand was the key technology to use because it was just faster. And it has some other properties. But we're seeing a convergence of where InfiniBand is from a bandwidth perspective as well as Ethernet. And so there's some interesting questions on how do you commoditize that. Now, when we talk about kind of silicon technology, processors and cell phones are driving the limits of how small a transistor is. On the networking side, it's about 5 generations behind. So they have several more generations before they start to hit the same type of limitations. And in general, the analog side is going to determine the speeds here versus the digital. So it's actually not necessarily that beneficial to go from a generation to generation. But that's kind of one of the interesting challenges of, okay, I need to have a fast network, I need to have low latency. How do I put those all together? And that's not only the hardware technology, but also the topology. And so there's some fun things that we can do there. All right, so the next thing to think about is data, right? So when we think about high performance computing in general, data and data gravity are a big issue. And so how do I think about the data that I'm generating? Where is it located? Can I move it? In certain cases, it's actually better to physically move data, storing it in hard drives and transporting them by your favorite courier than actually sending it over the wire. And so just an example, when HCL was built, it was creating 1 petabyte of data every second, right? I mean, that's just a massive amount of inflow of data that you have to store and then analyze over time. And if you want to do that analysis somewhere else, data transport now becomes a significant issue. So how do you think about dealing with data? And the nice thing is some of the technologies have basically evolved and kept up with some of the densities, but we're creating more and more data and not able to actually process it in time. And so just to demonstrate that, what I have here is a slide showing in 2019 and 2020 what happens in a minute, right? I mean, this is extraordinary, right? So you have over 700,000 hours of video from Netflix. You have Facebook at 1.3 billion queries in logins. You have all of these different components where this process is just exponential in the context of how much data we're generating or consuming as a global entity. And so behind this is the storage side, right? And looking at disks, whether they're hard drives or solid state, they give us different properties. But just to kind of put this in context, in the beginning, in 1956, we look at IBM's first hard drive. You couldn't buy it, you could only lease it. I think the density per square inch was 300 bits. And so when you think about this, we've gotten to billions and billions of bits per square inch today. And it's just amazing over that time how it's evolved. And we've gotten to today, you can buy a 15 terabyte disk for relatively inexpensive amount of money that's affordable. So we've gone from something that, again, this is the box. If you're ever in California near Almaden, so this is near San Jose, in the IBM lab there, you can actually see one of these machines, which is, a small refrigerator size. But this is something that you could not buy, right? You had to rent it, and it has less storage than your DRAM in your phone or whatever else. So this is an amazing thing to go from this size and density to today. What we have is the 15 terabytes in a hard drive, and we're getting even more densities in some of the non-volatile memories in the future. And that's kind of where it becomes an interesting aspect. Now, I'll end this kind of section with some thoughts on the different laws, because there's a whole bunch of laws that predicated or predicted what was going to happen. And today, most of them are broken. And so it'll be fun to take a look at those, and at least if you're not aware of them, you can look them up and we can go into more detail. But storage is obviously an important part, and you want to be able to build that. And the challenge here on this side with disks are, if you're doing random I/O, very, very slow. If you're doing sequential I/O, relatively fast. And so there's a whole bunch of methods to do that. Solid state drives, so your SSDs, whether they're NVMe or SATA attached, give you the capability to level the playing field between random access and sequential access, and so you can get almost the same type of bandwidth and speeds. What does that mean from a software perspective? Well, if I'm designing for disk, right, if you think about databases today, if I have an index that's over a certain size, usually over 1/10 the size of the table, I'll actually go through and scan the whole thing in versus doing random accesses. And this is just software that's been built to understand the hardware. And so these are the types of co-design things that when you then apply that to a solid-state drive, it doesn't match. And so we need to think about software in this context as well. All right. So we have this foundation, right? We have these technologies driving storage, driving networking, driving compute, driving memory, and we're seeing some of the barriers there, but those are the fundamental building blocks. And pre-2000, the big change was in high-performance computing, those were different technologies. And what has happened because of the investment in CMOS technology and scaling, there was a convergence of high-performance technologies and commodity technologies. And so we see this interesting aspect of the killer microprocessors taking over. And so that's an interesting thing to keep in mind. And now we have these new regimes where computer architecture and other areas are becoming more exciting because you have a bunch of different technologies to now think about and how do I optimize. I don't get with Intel every 18 months a faster, newer thing, and I don't need to change software. I actually now have to think about the software and the hardware, and this drives a lot of the co-design work that we're doing today. Now, shifting gears slightly, it's interesting to think about the applications in workspaces. So back in the 50s again, thinking about AI, what is artificial intelligence and how do we think about it changing our world? And fundamentally what had happened was we had these concepts of what AI can do, but we didn't have the computational capabilities to do anything with AI. And so that's where this whole inflection point has happened, where we can actually then now use AI to do a bunch of things because they now became tractable problems. I have the ability to answer questions in a reasonable amount of time. And so, definitions of what the machine can be, what it can simulate, notions of perceptrons, and then just defining machine learning in general. It's a massive set of calculations, and those calculations are fundamental to high-performance computing. Whether it's a matrix multiply or a convolution or what have you, same type of kernels, maybe different data type sizes, so 8 bits or 16 bits as opposed to 64 bits. But these are the fundamental components that drive all of these interesting ideas. And we're seeing much more research in how do we define the perceptron and use that in hardware. So one of the results of this is we've seen this progression of somewhat brute force techniques to more elegant techniques to actually solve human problems. And I think many of you may remember in the late 90s when IBM defeated the world chess player, right? That was a massive change and being able to say, we can have a machine that we can build. It can do a massive search of all the possible moves for the chess match and then figure out what the winning combination is and beat someone, right? So that was an interesting aspect. And chess is a restricted space, and so it's relatively straightforward to figure out where the inflection point is for technology to be able to do that. But that's kind of what they did, and it was an exciting place to see technology driving innovation and replacing what we can do, or doing it better, which is exciting. Now, this has some interesting aspects. When I take the evolution of all of the AI components, so I have time here on the x-axis and number of computations or operations per second on the y-axis, and that's a log plot, I'm getting this massive doubling starting in 2010 to last year of capabilities of AI. How much computational capabilities is required to solve these problems? So you have, obviously the chess components, but then going into AlphaGo and the ability to play and defeat a Go master. That's a huge, different challenge. But this requirement is obviously outpacing anything we've done before in terms of computational requirements, right? Before, the best case was we were getting, doubling every 18 months. This is every it's just an amazing amount of time. So that's what is driving part of our desire and need to have high-performance computing. And one of the results of this was the Tensor processing unit from Google. So they looked at all their AI capabilities and said, hey, if I use general-purpose computing, I think when Jeff initially looked at it, it's like, okay, I'm going to need 6 new data centers. So 6 data centers is a massive investment. They did some calculations and they created the TPU and then found out that no, I need 60 more data centers, which was outpacing the amount of data centers they had throughout all of Google. So when you look at that, that's an amazing kind of motivator to then build special purpose software. In this case, to do machine learning, they created an environment, TensorFlow, around that, and now they can run their applications on that. Now, when we look at the optimizations in terms of their models for looking at multilingual translation, as an example, I use Google Translate all the time. You could do this computation on a single TPU, version 3, and it would take 22 years to do that computation, obviously intractable. And so what they've done is they've thrown it and made it parallel, so if you can put 2,000 of these TPUs on it, you can solve that problem in 4 days. And so as you increase the capabilities from version 3 to version 4, you have this capability to do even more, which wasn't currently tractable. You'll see that with quantum and kind of post-quantum crypto as well. So there's all these interesting things to play with when you think about the overarching scenarios and what you have to build. And so, this is a scenario where you have 600 billion parameters. It's just a massive problem, right? But with co-design and being able to specialize, they were able to do that. And so the result, as I mentioned before, was in 2016, AlphaGo was able to defeat a grandmaster in Go. And Go is a much more difficult problem with a bigger state space, and so it was much harder from a computational problem to do, and it wasn't something that was easily done in terms of state space exploration. So that's a pretty big feat and a change in how we think about computing. But again, supercomputer style problems and results. So hopefully we've talked about some of the hardware, and I'll go through some of the laws in a couple slides. I want to just motivate, right? There's this new era of HPC, and we have everything from machine learning, deep learning, traditional high-performance computing, right? Whether it's NAMD or GROMACS, and visualization. All that's coming together to drive even more requirements from computing needs moving forward. So it's a great time to be, I think, in high-performance computing. And hopefully what you're seeing here, at least across these different areas, are different interdisciplinary components where you can look at, okay, maybe it's a medical application, COVID or vaccines or medicine. It can be modeling of atoms and creating material science type new alloys, or machine learning and deep learning, where I'm looking at analytics and those types of things. If we look at today's cloud, it is basically an interesting collection of supercomputers solving your problem. So every time you do a Google search or you're looking for some type of thing to buy, those recommendations are using massive amounts of compute to hopefully make your life better. And in the HPC space, we can actually direct it and do even more things, which is exciting. Now, what does all this mean from a high level, right? So it was kind of fun to look at these, look back at these areas and say, okay, well, what's kind of relevant? There's always a series of laws. Someone comes up with this observation, and then the question is, how long does it hold? So back in 1965, Gordon Moore made the observation that you could double transistor density every 18 months. And this really led to a revolution in compute. So this gave me this capability to just wait, right? And so if I waited 18 months, I'd get a new Intel processor, and it would be faster than the previous one. It'd give me more compute. And I didn't have to change any of my software. And so this led to the death, I guess, of high-performance specialized computing in different technologies. There are other issues. BJTs had the devices they used traditionally in high-performance computing had power issues, and so they hit the power wall first. But just looking at this, you had the same commodity technology that was driving it, but then you had this capability to get something better that was even socket compatible from hardware. I just take out the old processor, put in a new one, and life is good. That prevented a lot of work in specialized hardware because there was no point. By the time you developed your thing, it had to be way better than anything Intel could do to satisfy or to make it worthwhile. So that was an interesting aspect. In 2005, Dennard scaling stopped. And so as I decreased the transistor size in order to make sure that the electric field across the gate was the same, I decreased the voltage that I used to turn the gate off and on. What ended up happening was I got to a level where I couldn't decrease that anymore. And so what that meant is I couldn't increase the frequency. So in the late 90s to early 2000s, there was this whole frequency war. Who can get to a gigahertz fastest? Who can get the highest frequency? All of that was technology driven, and that kind of died. And so Dennard scaling prevented that, and we saw a shift from single processors that were fast to multiple processors that were not as fast. And this gave us the capability to work around Dennard scaling. In the context of the network, it's interesting to look at Nielsen's law, and this is from an individual perspective, so this is just internet bandwidth, what I can get access to. But they're looking at doubling the bandwidth every 20 months. And so we're seeing this massive increase, and we'll continue to see this for the next 5 or so years on the network side because it's generations behind the processors. And so it can actually continue to do this moving forward, but you're still getting an increase in the bandwidth. And then we have on the storage side this observation that you could actually double the capacity of storage. And so what I showed you in a couple of slides before was this 15 terabyte drive. The prediction in probably 2010 was we'd be around 40 terabytes. And so we've seen that slow down or taper. And so really what we see is all of these laws have some technology limits to them that we're starting to experience today. And so what we need is new materials, we need new technology to drive the next innovation of HPC. And the nice thing is HPC is willing to pay for it. So to have the best, the fastest, the biggest HPC funds those things, and it can trickle down to other stuff. So when we look at that in terms of these laws, right, this is a projection of Moore's law over time, starting in the 70s, and looking at the number of transistors. So you can start to see a slide off down here, not as much, it depends, but you see, single thread performance tail off, right? That corresponds to this frequency slowdown, the lack of Dennard scaling, and obviously translated directly into frequency. The power wall we've hit has stopped, right? So you don't get processors more than, say, 200 watts, 300 watts today. And so that's been capped in terms of what you can physically cool. And likewise, in 2005, we went from a single core to multiple cores, and that's been rising. And so you can see how technology transitions happen, and then what do we do next? And that's the big question. Likewise, looking at bandwidth to the home, right? Looking at that scaling over the last several decades is a similar trend. And it matches what we see in high-performance computing. High-performance computing is probably an order or two higher in terms of bandwidth and what you can see in the data center, but the trends are basically the same. And then finally, when you think about that, going from say, the late 80s to 2010, where Kreider's law was in effect. There was a nice linear scale on a log plot of density, and so we no longer have that. So that's kind of the fun part of all of this is historically we've seen a bunch of different components and rules being applied, and now we're seeing a transition phase, whether it's DRAM, disks, processors, all these things. And so when we talk about technologies today, especially in silicon technologies, we've gone from something that was physical, right? It was 10 nanometer or 16 nanometer, to something that will be marketing. So what does 5 nanometers really mean? What does 3 nanometers mean? There's probably angstrom equivalents, and so that's kind of the fun part. But how do we use that technology to our advantage? And architecture, software, code design give us that capability. So hopefully that gives you some kind of laws to remember, or at least things to look up. The slides will probably be available so you can get into more detail, but I wanted to provide a historical perspective on where we were so that we can see kind of in the future where we're going to go. So with that, I want to introduce BSC, at least to those that aren't familiar with it, and give you a sense of how we fit into supercomputing and what we're doing to drive technology there. What you'll notice is we're a national computing lab. We're funded by the Spanish government, the Catalan government, and UPC, which is the university where we're located. We have a bunch of supercomputing services, research and development, and we grant PhDs and masters in a variety of different programs, as well as doing technology transfers and those types of things. Just as a kind of, as of this July, we have about 257 projects running. These are grants from Europe, so Horizon 2020, from the Spanish government. We do research with industrial partners. All these are generally about 3-year contracts, so even though it's 130 million, it's spread over multiple years, and so that's kind of the fun part. In terms of ranking within Spain, we have a bunch of different contributions from the EU, and we're number 3, the top university. Now, what makes BSC unique, besides the supercomputer itself, which is the 5th department, is we have these 4 departments. There's computer science, which is the normal computer science space. We have earth science, so think about climate, the world, how that works, ocean. We have life science, personalized medicine, genomics, things where I could use high-performance computing to solve those challenges or answer questions. And then CASE, which is our applied engineering. So taking industrial applications and applying them high-performance computing to that. So think about modeling an airplane wing, or doing car crash analysis, so crashing cars without actually physically crashing them, doing the digital twin. So all of those things come together, and we have applications that drive this whole space. So we have a supercomputer at the bottom, we have applications and departments at the top, and those work together to do the optimizations in the space. On the computer science side, it's kind of traditional computer science with a focus on high-performance computing. Obviously, we have the high-performance computer, so might as well use that. So we want to do a leadership in high-performance computing on the software side, on the hardware side, really play key roles in that entire stack. And I say within the last 5 years, BSC has been getting more focused on the hardware side. So software has always been a big strength for the BSC, whether it's OpenMP or some of the other components, but really how do we actually build hardware that we can target for the supercomputing space. Again, right, whether it's parallel languages, all those things are really driving that. We have a bunch of work that we've done in visualization and program application understanding. And so right now, this is a very interesting space because we can say, okay, this matrix multiply is a key kernel in HPC. It's also a key kernel in AI. How do we make those work together and optimize? We don't want to forget what we've learned in HPC and not apply it in AI, for example. All right, so on the life science side, pretty straightforward, right? Thinking about how I can use machine learning for personalized medicine, drug discovery, protein folding. There's a whole bunch of different applications where we can use high-performance computing to drive innovation, research, and create new structures. And this is just listing a couple of them, right? So as you would imagine, right, computational genomics, text mining, all of these things that can be used to create a better environment and hopefully better outcomes for individuals. How do I create faster diagnoses, improved outcomes for patients, those types of things. So that's a pretty cool area. And AI is driving a lot of this. On the earth science side, right, what's happening with the climate? How do we do climate modeling? we're close to Africa and the desert. How do we do air quality? All of these things in terms of modeling. How do we model the ocean, the systems, the seas? So this really drives a bunch of different fundamental components, whether it's infrastructure development, agriculture, insurance, all those types of components that are critical to the economy. And then likewise, as I mentioned before, the case, which is the applied engineering aspect, looks at how do I do modeling from engines to hearts in terms of biomechanics, and driving a bunch of different components where there's really industrial applications of high-performance computing. So really training these SMEs, small and medium enterprise and large enterprise, to use high-performance computing better. And this was mentioned earlier, so I just wanted to say, hey, yeah, there's AI and machine learning, all those components in COVID, and so we were playing an active role in terms of the computation and driving outcomes, whether it's on the genomic side, storage, those type of things. So there's a whole bunch of different places where you can create models and drive that. And then fundamentally, right, we publish papers, right? So we're a research organization. Within the last 10 years, we've done almost 3,000 publications. Most of them are in computer science, but they also are in a bunch of other areas, and so those are fundamental pieces to that. Now, with this infrastructure, we have a lot of other capabilities which are exciting and led part of the components within Europe. So within Europe, there's a bunch of high-performance computing centers of excellences. The center of excellence focuses on different areas. So it can be in the case of performance and optimization of applications, the POP lab. It can be looking at Earth and Earth science, right? So we lead these four areas at the top, but we also participate in the next 8, and they have different domains of expertise where we can contribute. So this is where the life science, earth science, computer science case all work together to fashion what we can do and do more better in these areas. So that's kind of the fun part. Now with that in mind, we currently have about 100 students on the PhD track, about 45 on the master's side, and we've granted about 250 theses since the beginning of BSc. If you have great students, send them our way. That was my pitch in a bunch of different varieties. All right. I diverge and get back to HPC at hand today. So let's talk about high-performance computing as we see it today. At BSc, we have the MARINO 4. This is the 4th generation of machines. It is unique in the sense that it is 4 different clusters. So we have a primary cluster, which is all Intel general purpose processors. That gives us about 11 petaflops. We have a P9, which is IBM, plus Volta, which is NVIDIA, giving us about 1.5 petaflops. We have the ARM system based on the Fujitsu's A64FX, which is almost over half a petaflop. And then we also have an AMD system. So all those systems give us capabilities to look at traditional general purpose workflows, traditional GPU workflows, accelerators added to that from different vendors. And so it's a very unique space. A lot of other supercomputing centers are homogeneous, and so there's value in having to see this across the entire supercomputing ecosystem, whether it's worldwide. They have different machines, right? So there's not one best machine, and so having this heterogeneity within BSc gives us some of that representation. Now, just to give you a context, right, at the bottom showing, okay, MARINO 1 in 2004 was 42 teraflops, right? We doubled that in MARINO 2, did 10x in MARINO 3, and then another 10x in MARINO 4. And I'll show you some slides on what we're expecting for MARINO 5, which will be over 10x of what the MARINO 4 is, so getting around 200 petaflops. Now, BSc obviously leads in the context of supercomputing in Europe, and I'll get into some of those details later, but we also have within Spain a Spanish supercomputing network where we work with other universities and regions within Spain all the way to the Canary Islands to provide 14 different institutions with access to resources. So those might be machines locally as well as time in the BSc. And so that gives us obviously an opportunity to create even more widespread utilization of the system and from a research perspective enable more researchers, which is fantastic. And I'm showing a list of the partners down here at the bottom. And that's part of looking at it from a Spanish perspective. Now there's obviously the bigger case where PRACE is the thing that unifies Europe in high-performance computing. There's 26 members. There are 5 hosting members. We're one of them with the MARINO, and we're just showing all of them around in terms of France, Germany, and so forth. And that gives us a maximum current capability of about 220 petaflops. The next version of the pre-exascale machines, I think all of them at least will have around 200 petaflops, so we're going to significantly increase the capabilities of the system, looking from a European perspective. And so that's great, right? We're really driving shared resources, training, and scientific discovery across all these centers, and they have different focal areas in terms of what they're looking for from a research perspective. Now, obviously, there is overlap, so that's a good thing. Now, that gives us Europe, it gives us Spain. We're also driving research and collaborating with not only Latin America, but also Asia on the side of how do we increase and drive high-performance computing outside of Europe. And so RISC is that in the context of creating drivers for understanding how to establish high-performance computing in Central and South America primarily. And we have several partners in Europe working on that. There's a phase 2 as well, and so again, driving more collaboration. We're looking at how do we interface with the European Union and drive that forward to increase funding and collaboration. So this is more of a global view, not only with Latin America, but also with Asia. Now, one of the things that we've talked about, and this was actually in Lisbon in 2015, was this requirement, or at least view, that technology was becoming these isolated components where the US had its technology providers and some independence. China was developing the same capability and Europe was not. And so when Matteo was at this plenary session, he was proposing, for exascale, Europe needs to take a lead and actually drive development. And so that's part of the things that we've been working on, and part of the reason why we think open source ecosystems within HPC can help Europe get there. But this is, again, it's been a long time to get that going. Now, the nice thing is what we've seen at the same time, the previous European Commissioner was on board with that, right? And say, okay, how do we get there? The latest president, just in September, was saying, without building chips, there is no digital economy. And so how does Europe get to that point and driving that? And fundamentally, when we look at Thierry Breton, who's the head of the European Commission side, is also saying the same thing. So how do we drive technology? And what we're trying to do is give a plan for what does that mean, right? And so that's kind of the fun part. And so part of that plan was developing EuroHPC. This was proposed in 2017. Last year, I believe it just got off the ground. And so they're funding a bunch of different programs around HPC and have about 8 billion euro to distribute for this goal. And so in totality, that's not enough to do everything that you'd want to do to become digitally sovereign, but it is getting us closer in terms of high performance computing and at least doing demonstrators. And so part of that first round is MARINO 5, which I was talking about. So it's at least 200 petaflops. It is joint funded by the European Union in the context of EuroHPC, JU, that joint undertaking, and these consortium member states, Spain, Portugal, Turkey, and Croatia. So we're all coming together to provide the system. It's about 217 million. That includes the system and the operating costs for 4 or 5 years. And so that's an interesting aspect of that. Now, in that context, this still doesn't answer the question, right? What we will buy is stuff that's available today. So it'll be from Intel, from AMD, from NVIDIA, whoever has processors and accelerators available today. This still doesn't answer the question of building processors in Europe. So when we look at that, everywhere, watches, phones, cars, all have processors. And so when you look at it from that perspective, my life, your life, everyone's life is kind of impacted by technology. How do we present the same level of security, of features, of understanding in Europe if we don't build our own processors? And so obviously worried about security. A big issue for sovereignty is access. So we've seen with ARM and in China, this lack of access to technology, that's a challenge. And so you don't want to be in that space. And so the final part of that is how do we create a competitive supply chain in the EU for HPC and the rest of the digital economy. And those are part of the things that we're talking about. Now, if we step back a decade ago, just to keep this in context, we had this crazy idea that, hey, the cell phone chips could be used as a high-performance computing platform. That project was called Mont, and so we started off with Samsung devices at the time, put together a proof of concept to show how you can map technology to this, and then went through 3 or 4 generations to get there. And it was a very interesting aspect because we had partners on the hardware side, obviously ARM, Bull on the system integration side, so forth. And when we looked at this, we could do changes to the software stack, right? So system software applications, industrial applications, but because the hardware was fixed, we weren't able to do anything there. So, you know, out of that, we couldn't get an ARM-based GPU, for example. That was something that would have been nice, but wasn't possible. So in this context, we saw this nice software design component, but a lack of hardware design, and that's where the proprietary operating systems and, proprietary software or hardware gets in the way. So how do you bridge that gap? Now, the interesting thing starting in 2010 was we had this roadmap of how ARM became an important contributor to high-performance computing, and at the time, everyone thought that was crazy, right? I have a Watt processor going to compete with something from pick your favorite vendor, Cray, Intel, whoever. Now, the interesting aspect of this was Japan basically took up the gauntlet and said, hey, we can do hardware-software co-design with ARM, and we can build the A64FX, we can base it on what Riken is doing for their supercomputing center, and we can come up with something that's compelling, right? And so this is really looking at how do I do this combination of design that gives me something that's general purpose as well as specialized. And so out of that, this post-K processor came. So this is the A64FX. It has multiple cores, it has separate OS cores, it has vector capabilities, so I can issue one instruction that will do 64 elements, 128 elements, 8 elements. It's, you know, a process where I can play with the number of elements per instruction, so I can get an efficiency there. They don't do as much as 64, but that's interesting. They integrated HBM, and so they have really high bandwidth memory, and so your memory-bound applications are now faster. And they have their own specialized network that they put together, which they call TOFU. So I have a general purpose processor with GPU-like performance, and the amazing thing is for the last 18 months, actually more than that, it's been the top system listed in the top 500. So we'll have supercomputing is coming up in November, so I'll do another iteration of who is the top machine, but so far it's had 3 consecutive cycles of being the top machine. And so it's very interesting to see what they've done with what a general purpose processor is. Now, they do multiple levels of integration. So they have integration in the processor in terms of the number of cores. They have integration in the module, and then basically they start building up to the rack, and then multiple racks. And so, you know, this is almost 160,000 nodes, which one CPU is equal to a node, one of these little guys here. But that's an amazing amount of interconnectivity to get to that point and build this up, and we'll see how that continues. And this is a system that they can scale. So that's a really cool scenario. Now, kind of to take this all together, right, what I've talked about at the software level is a collection of applications from the OS up that are open source. And Europe has led on a lot of that development, whether it's GROMACS or Linux or what have you. This gives me capabilities at the application level, libraries, schedulers, tool chains, all those things to be able to modify and design and adapt software to what I want, where Linux is the de facto OS. Right, and so we'll continue to see that moving forward. And the nice thing about that is it gives me a landscape that's everything from high-performance computing all the way down to IoT if I look at kind of the same software APIs that the operating system gives me. Now, I get a common platform, specifications, interfaces, all those good things, and I can crowdsource who builds this, which is fantastic. One of the challenges we have, though, in software is fragmentation, and so we've learned from previous generations of at least being aware of that and ways and technologies, techniques to actually try to avoid it. Now, OCP is the Open Compute Platform. This is a group of hyperscale, so cloud providers that want an open hardware ecosystem from the physical standpoint. So how do I build servers? How do I build storage? They have pushed out a bunch of specifications and designs in that space. But when we get to CPUs, GPUs, and ASICs, it's not open, right? I can't talk to Intel about their hardware implementations, and from a research perspective, I can propose ideas, but I can't get them implemented. Intel obviously has to do that, and so I can't get a full life cycle. And this is an inhibiting factor in terms of doing this hardware-software co-design. So what do I get today? So on one end, I have this NVIDIA A100, right? It's an amazing piece of hardware, right? 54 billion transistors, the die size over 800 square millimeters. It can do teraflops of operations at 64 bits, all the way down to 32 bits and getting to over a terop at 4 bits, looking at how I deal with tensors. This system today is power limited. So they cap the power at, say, 400 watts. It can probably go up to 600 watts, but you can't cool it. So this is an interesting place to be. But NVIDIA does a fantastic job of putting out new hardware and pushing the envelope within their specialized environment. And so that's an exciting place to be, and I think this gives you one end of the spectrum. There's another end of the spectrum, which is even more exciting. Cerebras put together a wafer scale engine. So you took an entire wafer, right? So this is, a massive dinner plate, and they've created a system that matches and maps to that. And one of the reasons to do that is to get rid of I/O power between these different components here. If you think of each one of these as a little tile, you can do much less energy to communicate tile to tile if it's on wafer than if you have to go off chip. They're on their second generation. So it has amazing kind of specifications. They've gone from 16 to 7 nanometers, a massive area, 2.6 trillion transistors. I mean, that number is incredible. And then obviously lots of cores, lots of on-chip memory, gigabytes versus megabytes, massive amounts of memory bandwidth, both inside in the die and off, and so that's an interesting aspect there of this whole system. Now, putting these two things together, and let me first state this is not a fair comparison before I even go to the slide. But just getting the numbers right. So I'm comparing an entire wafer to a single A4, A100, right? And so in that context, you see these massive scales in terms of improvements from the Cerebras side. Again, small die compared to a dinner plate size thing, right? So please be aware of that in the context. But again, right, 1,000x improvement in on-chip memory, going from 40 gigabytes down to 40 megabytes, right? So this is an amazing just kind of way where technology is pushing this. Another interesting comparison, which I didn't do today, Tesla has the Dojo system. Again, they're looking at using this to do training for self-driving cars. They do packaging at the die level and create a package, overall system that's almost the same size, or at least it seems like it's the same size as the wafer. So again, there's different benefits to one pass or the other, right? The yield on the die, the yield on the wafer is going to be impacted by imperfections and defects, whereas the yield on an individual die can be higher. So if I do this and slice it up into dies, then I can actually compose a fully functional system, whereas Cerebras has to deal with functional defects, and their system does that. So that's kind of the fun part. So, but from an architecture perspective, very exciting. How do I map AI applications on top of these things? And the crazy thing about this is a system that's targeting AI, right? Now, when we look at their kind of lighthouse customers are, or at least the ones they're showing on their websites, are high-performance computing centers. So it's an interesting kind of intriguing first adopters problem where they're using hardware that's not necessarily traditional high-performance computing, meaning it does 32-bit operations versus higher precision 64-bit operations, but they're still targeting the same customers, and we'll see how that continues to go. Now, just interesting to look at these differences and how technology enables different things, but if you think outside the box, sometimes you can come up with solutions that are very intriguing, and we'll see how this startup does. in general. Now, why is this important, right? So if I look at high performance computing and efficiency over time, what I basically said in terms of the exascale challenge is how do I get an exaflop, which usually means running LinPack, a matrix multiply kernel, in 20 megawatts, right? So it's a completely artificial boundary. I've said, okay, I'm going to allocate 20 megawatts, and you need to run this application at this performance. So what ends up happening is if I map the performance of the top 500 in this blue dots here, is they basically get a 10x improvement every 4 years. What that means is I have to improve the energy per operation as well. And for an exaflop, I have to get down to 20 picojoules per flop. And of course, this needs to decrease by 10x every 4 years. So that's a high challenge. Now, the interesting thing to note is if I just want to move 64 bits, 1 millimeter on the chip, I'm already at 2 picojoules per flop. So data movement now becomes a critical challenge. And how do I do compute at the right place at the right time? And how do I maximize my efficiency? So, as we move further along, every time I have to move data, whether I use it or not, there's a penalty associated with that. And the more penalty I pay, the less efficient my system is. So data movement becomes a big challenge. And obviously, HPC is power bound as well. So just like your phone, you have the same constraints in high performance computing. It's just a bigger input of power, but still limited. So this all is an amazing opportunity for us to then think about how do I redesign the systems and get lower, more energy efficient systems, knowing what the trends are and moving forward. And so right now the question is, how do I build the next zettascale system, right? How do I do 1000x of the exaflop? Like the exaflop systems are here. Like just take that for granted. They're going to be deployed maybe this year, definitely next year. How do I get the next 1000x? And those are the questions that we're asking now in terms of building systems. Now, putting this all together for the technology trends for today, I have this massive penetration of open source software, right? And it's everything from IoT, Arduino, those types of things, down to Linux and HPC and all the applications around that. So we want to take advantage of that. Hopefully what I've shown you is with the issues of power and Moore's law, I really need to specialize. And creating these specialized systems gives me more performance. It's more cost effective, less power, all those good things. And this is really driving this hardware-software co-design phase. So how do I design for a set of applications, application-specific hardware, that when I put them together gives me something better than what's off the shelf? And so really what our solution to that is looking at combinations of, in research, what I can actually build. So RISC-V and Open Power give me this capability to drive hardware and design with software. And that's where this open source momentum is coming. And what I'll do is, in a bit is talk about how that is working with regard to RISC-V in particular, which is what we're using a lot of today. So fundamentally, what does that mean, right? In the future, I'm going to have a bunch of customized blocks that I'll put together. Some will be more flexible, so on the CPU side. Some will be more energy efficient or less flexible on the ASIC side. And I'll map a bunch of different components to that, whether it's TensorFlow, different types of engines, those types of things, to create that custom high-performance computer that I want. But I need to be able to do the analysis of the software. I need to be able to have the flexibility to change the hardware and put those building blocks together. And from a research perspective, that's the exciting part. With an open source ISA, I can build the hardware specific for my software, do that demonstration, and hopefully in the future, someone, company or whatever, will take that up and because we've built the hardware, says, yeah, that actually works, and drives it ahead. We're about halfway through. So I'm going to open it up for any questions there might be. And then if there are none, we can take a break. But I've gone through a lot of high-level stuff, so let me pause and see if there are questions. And there's a microphone, and there might be stuff online as well. I'm open for it all.
Thank you, John. Shall we go for a break? Do you want to? What do you prefer?
I'm going to stop because I've gone through half the presentation.
Yeah.
So I'm happy to go through for a break and/or answer questions. Both. We're at least doing a break. If not, questions.
So let me check if there's some question now, because after the second part, maybe some of this is already in the back of our heads. So online there's no questions so far, and from the audience, you have one? Okay.
Gonna make you walk all the way to the back. We can ping pong back and forth.
Hello, good afternoon. Thank you for your presentation. So I've worked before in HPC context and with energy efficiency, and at the time we already talked about the 20 megawatt hard bound. I wanted to ask you if you see any perspective on that bound getting softer, or that is to stay, that 20 megawatts limit.
It's interesting because there's a couple of different things with a 20 megawatt limit. One is just power delivery and density within a space, and so that's one challenge that you have at that top level. This is all not technology driven. Let me start there. In some cases, you'll see that there can be insurance limitations on how much power you can deliver to a place. So you have, okay, utility, how much can I physically deliver to my location? I have insurance on how much I can actually then deploy from an equipment perspective. And this really limits you to this 20 to 25 megawatt space. If you go over that, then you actually have to create a new building, which is kind of a crazy thing to think about, but that's a challenge. So really, it's from a practical perspective, what can I deploy? When we look at the new MARINO 5, it's going to be in the 20 megawatt delivery envelope for the data center. And I think that's pretty consistent both in high performance computing as well as the cloud context. So you'll see kind of 20 to 30 megawatt stamps put down. And in some cases, if you need more computing capabilities, you might actually build a data center right next to each other because of that. And usually that's like an insurance problem more so than anything else. So those are the challenges in terms of building it out and why we don't go beyond that. I mean, I think in general it's good to have these targets. And so for the Zetascale system, is that also going to be 20 megawatts? From a practicality perspective, probably, right? And so then the challenge becomes how do I get that 1000x improvement in efficiency? And if it's smaller data set sizes, right, or smaller data types, excuse me, 4 bits, 8 bits, those are much easier to get to than, say, a 64-bit multiply, accumulate.
John, just a follow-up on this question. Whenever we talk about consumption of supercomputing, we're always thinking about the full consumption on HPL, which includes the computer itself, networking, cooling, you mean it. What about the optimization of the codes themselves to actually try to bring down the consumption of the system? Is BSC working on something on that front?
Yes, there's a whole bunch of work thinking about optimal placement, energy efficiency. There's a project that we have, Energy Aware Runtime, which is really trying to optimize your system at an energy level in terms of how do I map applications, threads onto that. That's kind of one area which is I think, a big driver at BSC, and it's open source as well. There's a whole challenge in the context of noise. And so when I think about operating system noise, in cloud, this is the 95% tail latency. How do I bring that tail latency in so that I can have more predictable performance in the system? How do I guarantee that I can have different timelines, deadlines, and those types of things? So there's dynamic load balancing at the task level, which is driving that. And then you could layer on top of that energy awareness in terms of where do I place it. And as I mentioned before, this whole notion of data movement is huge. And so one of the projects I'll get into in terms of future research is really thinking about how do I attack sparse problems and how do I minimize data movement such that the data I'm moving I need versus adjacent data, which I call parasitic bytes. And so all that kind of comes together. But as you're alluding to, it's a full stack solution. It is, what do I do with the hardware? How does that implicate what I do with the software? How do I create mechanisms to translate programmer intent into things the hardware understands? So for example, a modern day processor has a bunch of branch prediction built in, right? It's like, which way am I going? There's a bunch of prediction across different components that try to infer what the programmer already knows. And so how do we create architectures and hardware that can co-develop and be co-optimized at that level? So all that stuff is important.
Thank you. Any other questions?
Thank you for the great presentation so far. This is a bit more of a philosophical question, I guess. You were talking about having the opportunity to start building our own hardware, which is nice because we are not going to be dependent on Intel and on closed source hardware. How much do you think, if we can do this, how much do you think that we need to change the way the software accessing this hardware is going to change? So, for instance, now you are seeing, for the storage part, there are a lot of frameworks such as SPDK to access directly NVMe disks. And so there are lots of optimizations for specific hardware. If we start building our own hardware, how much are we going to be able to change in the existing software? Should we keep using the same things and adapt the hardware to the software? So what is your perspective on this?
That is a tough area in general. And there's a layered approach to that whole process. The beautiful thing about high performance computing is that if you can demonstrate a benefit, people will rewrite their software. If I were to translate that into enterprise software, so your Oracle database or your whatever, companies are not willing to recompile. They're not willing to change binaries. You can change the hardware as much as you want, but if it has to run the same operating system, it has to run a bunch of different things. I mean, one of the funniest things that I experienced was, to this point, I would do data center tours, and we'd walk through and there's all this new shiny hardware, and then you'd see this Sun UltraSpark 5, which at that point was 20 years old, right? In the data center, in its little space in the rack, and you're like, well, what the heck is that, right? There was some proprietary software that only ran on that, and it had to stay there. So when you look at these things, that's kind of the challenge in the enterprise space. But HPC, if you can demonstrate I can get 30%, 10x, whatever, I mean 10x is huge, but even 30%, I think you can drive that. And what I'll talk about in the future slides is a scenario where you have to change the hardware and you have to change the software, and the combination of those two things give you benefit. So I think HPC is more amiable to doing that change, right? So that's the first part. And so then the question is, how do you do that co-design together? And I think that's the hard part, is really, when we look at, say, the POP Center of Excellence at BSC, part of that is profiling and understanding applications. From that understanding, how do I do optimization for the current architectures, identifying what the problems are with those architectures, and then designing something that can demonstrate that it can come together and work. And from our standpoint, the exciting part from our research side is I can now build that, and I can demonstrate that versus just do simulation. And so that's where now you can actually go through at a relatively inexpensive way. It's not a €1 billion investment to build a processor. It's millions to build a chip or something. And so that's exciting at that level. So I think that's what we're driving to. Now, your secondary question is, well, how do I plan for the future? The ISA gives me a contract with the hardware to say this is what I need to be compatible with. So I need to have a mechanism to support current software, and then through research and development demonstrate how I can transform that software into something that runs on the future hardware. So I want to have some legacy capability, some backward compatibility. The operating system gives me that. The ISA gives me that. But then for new features, I want to be able to enable that with the compiler and all those other things. And so I want to be able to do both. So I don't want to throw away all the old stuff, right? I mean, if you look at BSC, 80% of the code is Fortran. I'm not going to change that anytime soon. I am excited about some of the new codes on HPC, some of the task-based things, and they're doing task-based components, you know, whether it's task-based for Apache Spark or TensorFlow or whatever. They're doing similar things for OpenMP MPI as well. So we're seeing some convergence of these things, but you want to be able to say, I can run the old code in a mode, but then that same thing will be better if you make those changes. And that's what we're trying to do from a hardware perspective and a software perspective. But that's hard. I mean, that's just a fundamentally hard question. So making you run in the back now.
You have one. Okay.
But a good question. Software, you know, what we build from a hardware perspective is useless without software, right? And so we have this chicken and egg problem in general.
Thank you for the talk.
Sure.
I think this question is related to the 20 megawatt question and also this one about scaling HPC for the far future. You know, you mentioned transistor sizes are, you know, as low as they can possibly, maybe as low as they're going to get. Are we going to keep scaling HPC with classical computing? Are we going to move to quantum? And when we do, is that going to break the abstraction chain upwards? Because then we have different abstraction layers on the software level. So I guess the question is, how far can classical computing scale up? Where's the limit? When do we need to change the machine?
So, so many things to talk about. So I think at the high level, what I would say is think about quantum computing as just another accelerator, right? So I have the GPUs, I have whatever else, neuromorphic, and I have quantum. And for a class of applications for quantum, they're fantastic, right? And I'm not going to change that, not try to beat it. Quantum has its challenges, error correction, stability, blah, blah, blah. But let's just assume in 5 to 50 years we'll figure it out, right? And I don't know if it's 5 or 50, but somewhere in between there. So think of the quantum as an accelerator that we still need to interface to. We still need to get data from the classic digital world to the quantum world, and that's going to be a classic computer. We still need to be able to handle the amount of data it's going to consume or generate. So all of that stuff is still in the classic realm. And so there's technology that needs to be built out there. As I was showing in the previous slide here, right? Well, it's not shown there, but it was basically, I'm going to build a set of targets for the applications I'm going to run. So if I'm doing something that's, you know, crypto related or factorization related for quantum, I'm going to use that. I'm not going to do it in a classical case because it doesn't make sense or I can't physically do it, right? I mean, that's kind of the whole quantum supremacy component there. So that's that part. In the rest of the system, there's still going to be space where other types of compute fabrics will make sense, and those can be based on generic CMOS. The question that I'm interested in is what's beyond CMOS. And I think that's the interesting kind of technology foundation that then once we get that piece figured out, and you know, there's 50 years of development in CMOS to get it to where it was today. So it's not like it's a fast, cheap process. So once we figure out what the next thing is, how do we then leverage technology there? So an example of that within the last decade was a transition from spinning disks, so your hard drives, to SSDs. And it ate away at the top end first. Your high performance hard drives went away because the cost of the hard drive was more expensive than the cost of the SSD. And you couldn't justify that for a variety of different reasons. So those are the types of things where we'll look at, you know, high performance computing has the tolerance to pay for more things because it needs to be the fastest, biggest, best. And so we can implement it in high performance computing and then have it trickle down. And so that's an interesting question of what technologies will drive that from a manufacturing process to give us faster processors, higher frequencies within a particular power envelope. And you know, we don't want to build small nuclear reactors in a case, for example. Right? That's a limiting factor. Hopefully that answered your question. Lots of good stuff there going on.
Thank you. Any question from online? No. Okay, so thank you, John. Let's break for, I would say, 15 minutes.
Sure.
Yeah, so we'll reconvene at 50.
Sure.
Okay?
Works for me.
So 1750 here again. Okay? Let's have some break. There's something downstairs.
Are you ready? Yes. All right, we're good. All right, so mics are adjusted, everything. Welcome back to the second half of the talk. We're going to dive into how do we create this open ecosystem, and the first piece of that is really thinking about the Open ISA, in this context, RISC-V. I'm going to dive into that a bit and give you some history and show you where the momentum is there, which is super exciting. And then we'll look in terms of how do we build this from a HPC perspective with some of the research programs that are going on, and then the final pieces of that puzzle. So again, if you have questions, please don't be shy. Happy to have conversations and go from there. So remember, I had this whole diagram of my closed open stack. The software side was open in terms of applications and those components, and the hardware was not. And fundamentally what ends up happening there, if I kind of go through the animation, is we'll see a whole bunch of different applications like Romax and AMD and those types of things at the application level, which are open and customizable, and there's a bunch of work going on a variety of different places. That's supported by a laundry list of libraries, and I'm not going to go through all of those today, but these are fundamental building blocks. And one of the interesting things for me was we were looking at some financial codes, and in the bottom there was a call to BLAS, right? So it was a BLAS library call, and you wouldn't think about that in financial codes, but it's the same BLAS call that you'd see in an HPC code. There's a variety of schedulers, whether it's Slurm or other things, or runtimes like OpenMP. And then we have the actual tool chain. You might be a GCC fan or LLVM fan or both or neither. They both exist. And then you have debuggers and all those types of things. And fundamentally, we're running this on Linux, and there's various flavors from various folks. And then, as I mentioned, from a RISC-V perspective, you can see what software runs on RISC-V. So that's this GitHub link. And more interestingly, I'm going to talk about the RISC-V ecosystem for high-performance computing, which is a test bed to compile codes and see if they just compile, right? That's kind of our first step. So one of the big questions is, why would we want open source hardware? And fundamentally, having that from a software perspective, we can leverage a huge ecosystem and create compatibility across it. So the open source hardware gives me a contract where everyone can agree, and the ISA gives me that. If it's open, it's fully auditable. I can look at it. I can look at all the IP. I can make sure that I understand what's going on. From a safety perspective, there are no black boxes, no embedded codes. I can design for the size, weight, and power envelopes that I want. It's fully customizable. And this gives me that capability to do the software hardware co-design, which is critical for all these things. The nice thing about this is I do get the performance. I can create state-of-the-art implementation, so I can separate the implementation from say in 5 nanometer or 7 nanometer from the actual development. There's no vendor lock-in. I have a full ecosystem that I'm building. And then one of the big things is sovereignty. So there's always access to open source, which is great. And then fundamentally, the huge thing is community, right? We have a community that's worldwide that is open to collaboration. This will provide faster time to market, faster time to research, and really leveraging open source software in the same way that you do with open source hardware. That's the overall goal. Now, borrowing these slides from the RISC-V Foundation, there's a whole ecosystem, and what I've done is I put the ISA at the center, but you have a bunch of different software components up here with different target markets, whether it's HPC, consumer, IoT. There's a bunch of build components, the RTL, the description language, design verification, implementations, all the way down to silicon and soft IPs on this side, a bunch of services, and then training and tools and all that kind of stuff. So together, all this stuff gives me a capability to build systems from a research and a commercial perspective that are very useful. And we're excited about it from the research side, right? This is really giving us a capability, a tool to demonstrate our ideas. And then they're more believable because they're done in silicon versus in simulation. So all this stuff is very useful. And the ecosystem is driving that. On the ecosystem side, there's more than 2,000 members to RISC-V. Actually, that number is growing all the time. RISC-V is a very interesting space. So if I look at RISC-V, there's a bunch of chips and cores out there that are available, over 100 of them, that can be either an SoC, an IP, or something in an FPGA. Where the weakness of the system is on the kind of system side, so memory, network, drivers, components like that. If you were to look at power, power is the other side of it. Power has probably 3 processors. This is the open power, but they have 100 associated IPs that support it. And so the SoC part of power is very strong. The core part of RISC-V is very strong. And of this, when we look at this, over 1,900 individual members. So again, really community driven from that perspective. And so, that's a very positive thing, and the numbers keep growing. So over 100% growth in 2020. So that whole doubling process is very exciting from a community perspective. And the challenge there is how do you direct the community to create usable items of IP, of shareable things without fragmentation that we saw in the early days of Linux. So that's a challenge. Now, the interesting thing is by 2025, they're expecting 40% of these applications will be designed, the application-specific ICs, the ASICs will be designed by the OEMs, and that's an increase. And so RISC-V gives you that ability to do the customization. So unlike something you buy off the shelf, you can say, I need 5 of these widgets connected to 2 of these widgets and build that together and create a single chip for that versus having multiple components. And so that's the big win from a design perspective. It's an open model, right? So we're really looking at a free and open use case for this. The ecosystem drives this. You can do a bunch of different implementations. And because it's open, as I mentioned, you have the transparency and the security components. And from a business perspective, you get rid of the licensing fees and those types of things that you traditionally have with IP. I like to have these conversations where we're transitioning from an IP ownership regime to an IP delivery regime, and you get value add for delivering the IP. Most of the effort is actually on the IP delivery side when we deal with these large, small geometry chips. And so that's pretty exciting, but it's going to take some time to transition hardware companies into this notion of IP delivery. We already have this in software. Red Hat is an IP delivery company for something that you can build. They get benefit out of support and maintenance and providing you a binary. You can do the same thing in hardware. So on that front, from strategy and analytics, 50 billion connected and IoT devices, right? That's kind of the low end of things in terms of where these processors can fit in the embedded space. And so what I'm showing here is that graph of how that expands over time from now until 2025. And the question is, how much of that will be captured by RISC-V? There's a significant portion, right? They're already shipping over 1 billion cores in a bunch of different small devices like hard drives. And so this gives you a very exciting place to be. And then fundamentally, overall, the number of cores by 2025 is looking at over 80 billion. So we can adjust this and play with it in the high performance space. I mean, it's a useful component to drive this open ecosystem and create this new open era. So when we look at this, right, what makes it open? So there are 60 plus working groups. There are over 4,000 people contributing to those working groups, a bunch of different solutions. There's 29 local communities with over 5,000 engineers, right? And this is continuing to grow. And so this is embracing the complete open ecosystem and driving a bunch of innovation and technology. And the key thing there, which I'm excited about, is can we get to a point where we have an idea, there's something that's close to that in the sense of a base building block. I can tweak it in a month and come up with a validation of whether my idea is good or not. I think that's the exciting part, right? And how do we get there? So specifically, this was all RISC-V, right? There's a whole bunch of work that's being done, and RISC-V started out in the embedded space. So, what are we doing for high performance computing? So one of the things that we did was we created the special interest group for high performance computing, specifically to address features and topics within RISC-V targeting HPC. And really driving that. The overall mission is really the technical and strategic imperatives that guide the RISC-V ecosystem, and hope that we can develop this open HPC ecosystem, right? That's really what we're there for, whether it's talking about software, hardware features, those types of things. There's a bunch of work to get to being on par with the rest of the industry, and we have the flexibility from an open ecosystem to drive beyond that with new innovation. And so with that, the mission really is to take this broader set of new software, hardware opportunities and create something that addresses high performance computing from the edge to supercomputers, right? So we want to make sure that that part isn't forgotten. It's very clear that RISC-V is going to be a part of the embedded world. It is today. But how do we make sure that it can run the legacy codes and the emerging new AI, machine learning, and deep learning codes? And so that's part of the drive there. And we're really driving this open era for HPC, right? That's how we see it. So it can be anything from CPUs, accelerators, other type of co-processing units. It's stuff on the build side, so verification, compliance, making sure you can get all those components, alignment with IP vendors and IP enablement. All of these things we want to make sure that we can invest in and have the community build so that you can get a faster time to market or to research. And so this gives us that global community that we see in, say, Linux today. And how do we surpass that success story, right? I think that's an interesting question to answer. So of the initiatives, right, we're guiding the community participating in high-performance computing environments. So we were a part of ISC. We do some stuff in ICS in terms of workshops and conferences. We're giving talks and trying to increase the visibility and make sure people are aware of RISC-V because most people associate it with the embedded side. In terms of some of the initiatives that we're doing, we're focusing on improving and coming on par with the current technology, right? So there's virtual memory and supporting 57-bit, 64-bit, and 128-bit virtual address spaces. This gives us both capabilities from a software perspective, like partition global address space, PGAS, security, all those things kind of bundle into the capabilities that currently aren't available on other architectures. We're developing a software and hardware ecosystem and roadmap so we can actually plan out and try to prevent fragmentation. There's a whole bunch of work on what accelerators we should provide, what extensions. The RISC-V vector extensions existed before the SIG, and that's an example of driving some HPC stuff within that as an extension. And then fundamentally, what I'll highlight today is some of the work that I've been doing with John Liddell on the HPC software stack. So it's great to talk about hardware, but if you don't have software, it doesn't matter. And so that's the fundamental piece of how do we start using technology to build that up for us, and we're starting with the high-performance computing libraries. So John's part of the Tactical Computing Labs, the organization out in Texas, and basically we're looking at these kind of categories of software, and we're seeing if they run on RISC-V, right? That's the base level. Can I compile with GCC and LLVM? So you have the app. Well, let's start the library side. So libraries are probably the easiest in the sense that's a more focused, smaller, tractable set of codes, right? So everything from FFTW, SLEEF, BLAST, those types of things, can they compile, right? And that's the first question. There's more advanced questions of can you auto-vectorize and those types of things, but let's start with just compilation. There's tools. Can we run XCAT, OpenMP, shared memory, GCC, LLVM? The actual infrastructure that we're using today has both GCC and LLVM, a couple different variants of that, where you can kick off a Jenkins job to then test both the compiler and compilation of the code. You get into benchmarks, which are a simplified version of applications. Can we run those and compile those for RISC-V? And obviously, in our case, also interested in the vectorization side. And then you get up to the applications, the larger code bases. So we want to do a pragmatic, stepwise approach to addressing the software ecosystem and understanding where the gaps are, what we can run, and then optimizing from there. So the first step is what can we build? The next step is fixing those problems, and then finally you go to optimization across a wide variety of ways and using the community to support that, whether that's LLVM or GCC. So fundamentally, there's two different flows that we're showing here for the Jenkins jobs, right? There's a GCC flow and then a LLVM flow. They basically both do the same thing. So I can take within the GitHub repository, drop in a library, and kick off these builds and see if the actual builds happen. The nice thing is I can also parameterize that build so I can have multiple builds in parallel. The front end is public, and so anyone can do a submission. The back end is currently in Texas, but anyone can add resources to this. So you can do cross-compilation, you can do native compilation. We're building up a series of different clusters at BSC, and I know John at Tactical has a couple of different clusters to actually do native compilation with the various dev boards that are out there. And so that's a nice thing, and then we can actually have a heat map of what works and what doesn't, right? And so that's key. To be clear, Fortran isn't supported by LLVM. There's minor support by GCC, and so that's a big hole that we need to fix. And in this context, Pacific Northwest Labs, which is part of NVIDIA, is doing the FLANG, the Fortran front end for NVIDIA, sorry, for Fortran. Once that becomes available, we can plug that into our version of LLVM and use the IR to then do auto vectorization, those types of things. So that's pretty exciting as you look at the community building process, but that's a gating factor for the Fortran codes. Now, when you look at this, right, there's a whole test bed, and this is on RISC-V-test.org, where you can have different projects. So these are the versions of LLVM, and they're building a bunch of different tests for that. And so that's kind of the fun part, and it's completely automated. It's very much like your other DevOps interfaces out there. And you can go through and create this public repository for the build. This is a little bit small, but you can see what it's building for, what binary, Clang, and so forth, and what the library is. So again, very straightforward and automated at that level. Now, as I mentioned, the test harness is public. It's live today, so you can check it out. If you want to drop in some of your codes to see if they're going to work, it will do that for you. And you can take a look at what's been building so far. So this is our first kind of big rock to move, is what is supported in that context. So when we look at that, right, building this open ecosystem with RISC-V, basically, if we're requiring, I've postulated that we require these customized hardware solutions. We now have a mechanism to do that with RISC-V. We can build the software on top of that and then create this global collection of individuals interested in building this and have HPC lead that technology, right? So we're actually reviving a bunch of technology from, say, the 80s and 90s, like vectorized compilers, and bringing those in and making them mainstream. And fundamentally, all these pieces will help to accelerate the research, innovation, and development across that. And as you can see, the RISC-V ecosystem is growing immensely, so that's pretty exciting. So that's really the basis. If I look at open source today, I have something that's not associated with a company, growing rapidly, we already see uptake, and so then how can we use this in a broader context, in this case in high-performance computing. So how do I build this, right? I have all these ingredients. I need to do specialization. I need to have the software stack. I need to have all these components come together. What does that mean, right? And so when we talk about this, it's a very interesting challenge because we really want to step back and say, okay, well, what does my European software stack and hardware stack look like? In this case, I've labeled the European Open System Stack, and I've defined these TRLs, technology readiness level. 8 and 9 at the top is product worthy. 1 and 2 is kind of concept or pre-concept. And so I wanted to try and classify just at a broad level the span of capabilities within Europe on these things, right? So we really don't have a high-performance computing processor vendor today, right? If you ask me about embedded, I could point to NXP, Infineon, Bosch, a bunch of folks, ST, right? Just to name a few. I'm not trying to pick on one or the other, but just to give you some. There are some accelerators in the UK. We're seeing some neuromorphic work. There's some quantum stuff, although we're kind of lagging there. But as I move up the stack, I get to other things. Like if I think about building boards and doing integration, I can point to Atos, Spol, I can point to E4. There's a bunch of companies that do that. Where Europe really leads is on the software side. And so whether it's system level, it could be storage, like BGFS, all the way up to the tools and the applications like Romax, those are really driving that. And so I can now take those and compile them, but I also want to map them to the hardware, which in this case would be RISC-V. And so one of the challenges is, what do I do to do that? So when we were talking about that at BSC, we needed an internal structure to actually make this happen. There wasn't anything that gave us the capability to drive innovation at the full stack level. And let me show you what I mean by that. So as I mentioned before, at the top, we have these application areas. So life science, earth science, computer science, and case, those are really driving different application specialties within the supercomputing environment. I'm showing here the MARINO 4, which is our supercomputer. So we can run those there, right? And I have a way to run these applications on predefined hardware. There wasn't anything that really gave me the capability to then do hardware-software co-design where I took the application characteristics, I designed some hardware for that, and then it lands in the MARINO. And so that's really what we're trying to do with the Laboratory for Open Computer Architecture, or LOCA, is be able to go through that whole process and have a place for it to land. And I think that's one of the most important characteristics of what we're talking about. It's not just saying that we need to do this, it is in the next version of Mare Nostrum, this is where it can go and there's a place for the hardware, and we've already optimized the software. So what LOCA is this mechanism to extend the open source ecosystem into hardware, to bring the capability of building hardware to BSC and the rest of Europe, and really create an ecosystem where we can work collaboratively in this space, not only with other academics and researchers, but also in the context of industry, and bring that whole kind of training process back to Europe. So this provides us ideally within a repository of silicon-proven open source usable hardware. It's a great intersection with industry and academia, and really creating this, think of a repository for the European open system stack. And bringing a higher level of integration, more complexity into the ICT industry. So how do we build high-performance processors and accelerators in Europe? How do we train the students, both on the software and the hardware side, to do that? And then fundamentally create that incubator for open source IP, right, and have it being European. One of the things that we thought about when we did this is there's this beautiful process that happens in Catalonia in September for Marseille, and they create these human towers, or castillers. Those are a bunch of people at the base, so there's a lot of people at the base, and then you have a few people stand on their shoulders, and you have a few more people stand on their shoulders, so forth and so on, and it can get really tall. This was a great analogy for what open source is, right? We have a massive collection of folks that are building some common tools, and then small groups can create these spikes of innovation where they can build on top of that. And so that was the genesis for the logo in the context of LOCA, is really taking that kind of specific Catalonian thing and seeing that analogous feature within open source. Now what that means is we can create a traditional master apprentice environment for teaching people how to do high performance design in low geometries. It's really creating this ideal sandbox for innovation and creativity, where we can do things that are more risky from a research perspective, bring in industry veterans that are more used to doing conservative designs, and meld those two things together. And so that's kind of the fun part. So that's really what LOCA is there, is that mechanism to get us there. And we see that as something that can be broader from a European perspective. Now, in the end, what we're trying to do, and what I'm showing here on the left, is the different levels of kind of performance within your system. So you have embedded IoT, those are, in your smartwatch or thermostat. You have mid-level general purpose processors, or GPPs. This is your laptop or desktop processor. High performance computing accelerators, and then high performance server, usually dual socket chips. So that's kind of the spectrum of development that we have to go through, where in the end we want something in this upper right corner, right? That's what we want. And to get there, that's what we're talking about, right? So we want to be able to build something like, in this case, just a processor like Fugaku, right? So I don't need accelerators. Or in the case of x86, Intel or AMD plus their constituent accelerators or GPUs. And furthermore, we're saying, hey, Mare Nostrum 6, that should be the target. So it's not the case that we're just saying, yeah, someone should do this. Like, no, we need to have a target and drive that. And what we're doing from a research perspective is building from the ground up, right? So we're starting off with things that are in the embedded space, and we have a project like DRAC, which is building out these processors and actually going through and fabricating the chips. We're working on an eProcessor, a mid-grade two-way out-of-order processor, and I'll go into details on that. And we have the accelerators in the European Processor Initiative and some of the other supporting components that get there. And these are some of the partners that are key to working with us, both in RISC-V and on our particular projects. So by combining all these things together, and these are all funded projects, we can hopefully get there. And obviously BSC wants to be in the conversation about research topics within the general purpose high performance computing space. So this all is married together to create step functions to get us closer and closer to our objective, which is in this upper right corner. Now when we look at the ecosystem, right, it's fun. We're doing a bunch of different simple processors here. We've taped out one in May of 2019. We've done 2 more tape outs this year, which actually I'm not showing one, but that's okay. And then we're working on the e-processor project. And so these arrows show how we're doing technology transfer within our projects. So we're trying to take a broad view of what are the big building blocks for the system, and then how do we get more and more capabilities as we go from project to project and have continuity. So in the context of accelerators, we started off with EPI. We have 8 partners, I believe, working on RISC-V explicit accelerators. Those partners are in the second phase, or SGA2. We have a pilot that's working on creating more technology around the SoC. This is the Uncore, so think I/O memory, and building research prototypes that then can be used to demonstrate some cool technology. We have FPGA platforms we're using for emulation and software development that are focused on research designs that are further out in the future, and obviously the mid-level processor. So all that's coming together on the hardware side, but you also need the software, right? So as I mentioned, the software stack from tools and system software, we're starting off on the accelerated or embedded side because that's a very small slice of that. I can basically do a couple of libraries, have a lot less functionality, but still get the benefits from that, versus if I was supporting a general purpose processor, which has to run everything. So we're trying to be as pragmatic as possible when we look at these components. So we have this kind of stair-step process, right? Starting from EPI and moving up, how do we add more and more functionality and capabilities to enable the hardware design? And starting with EPI, this is the European Processor Initiative. There's about 28 partners from 10 different countries. The first program was 80 million euro in funding. And part of that, a small part of that, maybe 20%, less than 20%, was focused on EPAC, which is the EPI accelerator, which is composed of 3 different RISC-V accelerators. There's the VRP, or Variable Precision Core. This is coming out of Sewa, where they're using 128-bit or 256-bit operands, and so they're doing very high precision. There's a vector processor worked on by BSC, Semidynamics, and University of Zagreb. Those were together putting a processor, the scalar core C, plus a vector unit, which is an 8-lane vector unit, and there's 4 of those on the chip. And then STX is a stencil and machine learning processor from ETH, Zurich, and Fraunhofer working together. And that is then supported by a NOC, L2 memories, and those types of things. It can connect to a general purpose processor like an ARM core on a tile, or it can connect to an FPGA, and the test chip is doing that. And so what we have, what it ends up looking like is this component. So we have this ring of components with different functionality. It connects to an Uncore, and that gives us that capability from just a poor man's test chip, basically. So instead of having one test chip for each of the accelerators, we put them all together and created that whole thing, which is great. And it's in the lab being brought up as I speak. On the vector processor side, we have Avaspado coming from Semidynamics in Barcelona. It's a traditional processor, integer processor, and it uses OVI, the Open Vector Interface, to talk to an 8-lane vector processor. So the main difference here between vector and SIMD, I issue one instruction in one cycle with latency generally. I can get 4 or 8 operands operated on. In vector, I can extend that length beyond that. And so that one instruction might work on, in this case, 256 operands. And so I can do 256 floating point multiply accumulates with one instruction versus 16 or 32, or in the worst case, 256, if I think about it from a scalar process. And there's a bunch of control and components there. The vector lane itself has, the various components. I won't go into detail on that due to time, but that gives us a baseline. On the embedded side, we're looking at DRAC, which is a Catalan-funded project. And in that, we're looking at a bunch of different components. So there's genomics acceleration, post-quantum cryptography, auto-navigation, and as I mentioned, we did this first tape out in 2019. Very simple core, right? So it's a single in-order pipeline, 5 stages, small caches. It was done in TSMC 65 nanometer, so that's probably early 2000s. And it boots Linux, which is exciting. There's a second version of this chip where we added the vector unit to it. So there's these 2 vector lanes and the vector register file. And again, we're going through the process of integrating more IP. So it has an onboard clock, it has a bunch of debug capabilities with JTAG, all of these things to make it run faster and better, still in 65 nanometer. And the next tape out is in 22. So as I look at this, we have a roadmap where we go from Divino, which is a 65, to Sargantano, which is a 22 nanometer with some additional functionality, to an out-of-order core next year. So this is where it gets exciting as you kind of build up these stair steps and capabilities of both processor and software. Now, part of this is thinking about how do we think about the future, and that leads to the MEET project, which is an FPGA-based emulation platform for software development. So as part of the MARINO 5, we created a research project around that to create and promote a Made in Europe IP. Two fundamental basic building blocks. We want to be able to evaluate before we tape out IP, so the pre-silicon validation, at relatively high speeds and scale. And we want to have a software development vehicle that allows us to do something on the order of, say, 100 units, accelerators working together, and create the infrastructure around that. And so that's kind of the fun part. The research aspect of this is actually looking at the thing that we're going to use as a demonstrator. So what we created for MEEP was the Accelerated Compute and Memory Engine, or ACME architecture. It's a multi-threaded vector disaggregated architecture. And that's a lot of words. So what that means is we basically are going back to the early 80s where they had this access, decoupled access and execute architecture. So access, think of memory, so your loads and stores, and execute, adds and subtracts, what have you. Basically, you have two different cores or pipelines that do those things, and so we're using that as the motivator. And in this case, we want to run both dense and sparse workloads. So the dense workloads are just how many floating point multiply accumulates you have and how you can feed those appropriately. The sparse side is how do I manage memory, and how do I manage memory effectively? And so we both virtualize the vector register, we create a memory engine for sparsity, and we want to drive this towards high performance and data analytics in general. The other part of this is when I think of accelerators, I have a core, a CPU of some sort, and I also have an accelerator. We want to merge those two things together and create this self-hosted accelerator. So in that case, what ends up happening is we reduce the CPU load or CPU tax and ideally remove or reduce data movement so we can do those effectively. Now what ends up happening is we have three different components. There is the RTL that defines the ACME architecture. There's a software stack that runs on top of that, and we map the RTL onto the FPGA to run the software stack so we can actually do the experimentation and create this SDV. And so that's all that comes together. When we talk about the architecture at a high level, we basically have a sea of accelerators. This is these vast squares or tiles connected to memory tiles, and those memory tiles are interfacing to the memory controllers in HBM. In an ideal world, we'd also have non-volatile memory associated with HBM, and so that would give us the capability to have a much larger memory footprint and potentially remove inline storage that exists today in systems in high-performance computing. To get a little bit deeper, right, the main characteristics are L1 and L2 cache in the vast tiles, and L3 in level cache in the memory tiles. And really, we have these two big components: the compute side, which is really thinking about the scalar core and the accelerators. So we have the vector accelerator and systolic arrays, and those are traditional compute units that are used today, say in the TPU, like the from Google. And then we have memory bandwidth bound applications where we're really focused on the memory tile, where we have the second level or long vector register file, a memory controller CPU, and flexibility in how we use the on-chip memory. It can be used as a hardware managed scratch pad or as a hardware managed cache. And so this is some of the features that we have there, which is kind of fun. And this is completely research, right? This is not in any way driving to product. It's really focused on what can we do in, say, 2025, and how can we prove out these ideas with the simulation, emulation ecosystem. So what ends up happening is we drive a little bit deeper and we get into the vast tile, and there's organization of 8 cores with a shared L2 that's global. Within each core we have the scalar front end and then a arrangement of vector lanes which can be partitioned and scaled And so that's kind of the fun part. And there's also a custom fabric to communicate between the vector lane pairs, and that drives all those components. For the overall system, we're taking FPGAs. In this case, our initial ones are Alveo U280s from Xilinx, and we're mapping a portion of the accelerator onto the actual FPGA, and we're using PCI Express, HBM, and all the inherent components, hard IPs within the FPGA, and just putting in the other components for Acme. And so that gives us a very nice, easy way to get reuse and design only the core infrastructure that's required for Acme. Now, what does that mean, right? So we have the PCI Express interface that Xilinx provides. There's a controller, and then we have to provide a standardized interface. Likewise, for Ethernet or FPGA to FPGA controller and HBM, right? All of those have standardized interfaces where we can put anything inside that. It can be a processor, it can be accelerator, what have you. And so that's kind of reusable for other projects beyond just what we're doing. From the software stack, there's the traditional HPC workloads, which are here on the right, and more non-traditional data analytics, medical applications and frameworks on the left. And those are combined to then drive the co-design process that we're talking about. And then fundamentally what that maps to our system, right? So I have basically the improvements in the software stack going from left to right and the hardware stack. And so as we build up, we can supply the OS. This is our contract with hardware. And it can support containers, the runtime, system software, libraries, and applications. Likewise, we can produce the initial CPU and then go through, do multi-core, the entire VAS tile, and build all these things up, the memory controller CPU, as we have this research project develop. And then in the end, what ends up happening once I have this is I can then map this onto an FPGA. And that's how I get to Acme and then scale it with the traditional software that we have today, which is kind of cool. And so that gives me the accelerator and infrastructure not only for Acme, but say eProcessor. And in this case, this is a JU project, which we're going through and building application-specific accelerators for HPC, for AI, and bioinformatics. And we have different types of accelerators with different precision to provide that, with the base being this two-way out-of-order multi-core with adaptive caches, scratch pads, and some low-power characteristics. And so we see this in a scenario where we can create both an on-chip multi-core, so two cores and accelerator that's coherent, plus an off-chip coherent link, so think of your dual socket systems you see today, in an existing form factor from a previous project called Legato. This has 10 partners, and we're really excited about doing this first in the FPGA as an emulation target, and then in silicon. And the nice thing about doing the FPGA is now I can implement as one of the use cases an FPGA accelerator, because I've already built the interface. And so I can connect the processor to an FPGA, and that just works out of the box because of the way we've done our emulation. And so this will basically push forward the capabilities in the RISC-V ecosystem, and this will be an open source core. The next phase is what has happened with European processor initiatives is they've created two pilots, one for the general purpose processor and one for the accelerator phase. And we, BSC, is coordinating the European pilot, which is a full stack design, right? So what I have here is a software stack on the left with an HPC and a machine learning and stencil kind of thrust. HPC is normal things like GROMACS and EC Earth, the libraries, frameworks, and so forth, all the way down to the tool chain, and that runs on a vector accelerator. Likewise, on the stencil side, we have video processing, BERT, which is natural language processing, all the different components there running on the machine learning accelerator. Instead of having a single accelerator with both, we're separating them out and creating two different ones with shared infrastructure. This will go into a box, which eventually will test high performance immersion cooling. So we're going to liquid cooling on this platform and demonstrating that ideally with the general purpose processor from the other pilot, but it's agnostic because it's PCI Express attached. And so what that means is we have the sea of compute tiles, and those compute tiles can either be vector processors or machine learning processors, and we have a common uncore, and that uncore provides PCI Express, chip-to-chip C2C bridge, so this is for coherent connections, and LPDDR as the memory interface, and those can be integrated in a PCB or in package. PCBs are cheaper though, and so you can have a 4-way glueless configuration if we want. This project has 19 partners associated with it, which is pretty exciting. And so this is really pushing the capabilities of research, training, and eventually, hopefully, commercialization by some other third-party company, depending on who that is. Now, all of those things come together, and the second phase, or SGA2, Shared Grant Agreement 2 for EPI, is also on the horizon to be started. And fundamentally, that continues the work that we were doing in EPI 1. So when we look at that, we've done the first or the first instantiation of EPAC, version 1.0. We can do version 1.5, and that gives us the capability to fix any issues and changes on that side. And it looks the same as before, right? We basically do upgrades to the fix bugs and that kind of stuff to the tile. The Uncore is the same, and then we move forward with that and have a more functional, higher performant demonstrator. Likewise, we're doing a second version of the chip where we improve the on-chip ecosystem, more chip-to-chip links, so think about glueless logic and having more things combined, DDR, a crossbar, and the capability to have some test components. This would look like some of the I/O chips you'd see in today's modern architectures, like from AMD or IBM or so forth. Integration is the same, right? How do we put this into a package that goes into a PCB and say maybe an open compute platform? But fundamentally, that gets us somewhat closer to a working system where I can have both components, I/O chip and a set of accelerators. And so what ends up happening is we have this capability, as I've shown, to continue to improve the base level foundational technologies so we can get to this space. And I've been talking mostly about the accelerator side, but there's also some processor work in place. And obviously there's a lot more work to be done and funding around that, both from a research and a development side. But that gives us kind of a target to approach that, right? And that's kind of the fun part. So we have this whole notion of what that roadmap should be, and then how do we implement it from these projects' perspectives, and we're heavily involved in all of those things. Now, that gives you kind of some of the fundamental building blocks, right? And so I wanted to conclude with a few slides just to say, well, okay, I have all these disparate parts, how do I put them together to get something that's useful? And so really what we see for HPC tomorrow is this notion of opening up the RISC-V space in general with CPUs, GPUs, and ASICs. You could also use open power. It's questionable if you can use MIPS, but that is was a possibility. And so Europe has this opportunity to kind of design and define what we want and then drive the ecosystem in that space, and that's what BSC is trying to do with the SIG HPC and involvement with RISC-V in general. It gives us a whole bunch of components in terms of being open source. We'll have freedom of access, and ideally in the open source context, a whole bunch of other positives around that. And fundamentally, we see RISC-V as a unifying force. It is a contract for an ISA, which then says everyone will build and be compatible to that. That's really the power there. And we can have a common language to speak to industry about saying, I've built this chip, here's how it works, here's the ISA, here's the extensions, here's the custom instructions, what have you. You know, what do you think? And they can actually see that thing, which is awesome. Now, that's part of how we envision the future of here's the base building blocks and the technology around it. But we also want to look at the past. And so back in 2010, we said, hey, let's use ARM to build supercomputers, and we had the Mont Blanc project out of that. Hopefully what you've seen is there was this desire from Japan to take and actually own ARM, and then use that to drive with €1 billion in investment over 6 years, the #1 supercomputer in the world today, right? And so that's a very interesting aspect of being able to see this translation of research to deployment to success on that side. How do we do that in the context of Europe? And in general, we look at RISC-V as being that vehicle to get us there, and then fundamentally go from a buy scenario to a build scenario. And specifically, how do we build something for Mare Nostrum 6? So in the 27, 28 time frame, how can we build something European, accelerator components, what have you, that shows up in a supercomputer at BSC? So that's, I think, a very strong statement. And so we want to do the same type of thing. We want to have a research to product life cycle where we can do something similar to what they did with Fugaku or ECP in the US. This is their exascale compute platforms. Define paths from low TRL, so prototype and ideas, to product, and then basically link the two together. Right? So right now we do a bunch of research, but there's no tender associated with that research, whereas in Japan and in the US there is. So how can we create this massive investment of flagships or other things where I can link the research to a development and a tender, and then have that full cycle and go from this notion of research to HP systems and all the way to the tender, so we can get to MARINOS from 6 or some other set of computers in Europe. And that's, I think, the key there is really having that linkage. Once we do that, then companies involved in the research aspects can raise money for creating the products and then have enough funding to do that, because research money alone is not enough, right? We did the EPAC with about 14 million euro, right? That's not enough to build a product. If you look at today's accelerator companies in the US and the UK, 400, 600 million, $1 billion to create these accelerators. So we're nowhere close to the investment required. Now, to get to that success, I want to wrap up in the sense of how do we get there, right? Well, obviously we're embracing open source hardware and driving that to build infrastructure that can be shared within Europe and the world, and leverage the global ecosystem from that. We want to use that to jumpstart the ICT industry within Europe and drive both research and innovation and different funding instruments around that. For us, it's very important for us to teach, train, and collaborate, right? That's what BSC does as a research institute, and basically harness the global technology ecosystem that exists today. So we see folks around the world, China, US, Japan, all over Europe, embracing RISC-V, and I think this is a very positive thing. What this does require is significant funding, right? So we need to have focused programs and projects, both on the software and the hardware side, teams that can do the focused work that's necessary, and figuring out how to work with that within the European ecosystem, transitioning from a buy process to a build process and doing that strategically and pragmatically. But even if we look at a single kind of project to build a high quality accelerator or processor, that's on the order of €1 billion. And probably half of that's not technology money. So when we look at this, this is the challenge, right? It is kind of putting that together, getting the European Commission, Euro HPC behind that, understanding the investment. If we truly want to be autonomous, it's a decade away and at least €100 billion. So that's kind of the high level. How do we get there? So that's the fun part. With that, I will take questions, and hopefully you've learned some good things, both on the technology, politics, all of these things moving forward. Questions? And thank you for staying late.
No questions from the internet. So any question from the audience? From the...
Hi. Somehow two related questions. Okay. One related to the co-design and to have specialized hardware and the co-design with software. This applies to a very small percent of software, because there is a lot of legacy software. And how you see the software stack and the different building blocks and the opportunity to have in the LLVM, in the compiler, or in the libraries, some specialization for different hardware that at the point of the software in the application, you don't need to modify, and the legacy application can take advantage of this specialized hardware. And another question is, this co-design is most of the times geared towards performance, to be faster. But nowadays there is also a higher importance to energy and power efficiency. How can this also gives bring even more complexity to all this?
Sure, let me try to tackle those, and if I forget, please remind me. So the first question was really on the hardware-software co-design side with respect to software, correct? When we think about that, there's a couple of different things. What we're observing in general is this push towards productivity languages, so higher level abstractions where the domain expert can classify, write the application, and it will be translated. The problem with that is it's getting further and further away from the hardware, so there's no way to tie performance of the abstract model to performance of the actual hardware. So what does that mean? That means that we need to input a bunch of different things. We have the productivity layer, which is, you know, Python, Java, whatever. It could be domain-specific things, TensorFlow. And then we have an efficiency layer, which is going to then do the mapping of that high-level thing to your explicit hardware. And the challenge there is how do we embed in the language the capability to translate that knowledge to the hardware. So for us, vector architectures give us that capability. We can translate data structures and those types of things into things that we don't have to intuit or predict in hardware because they're already defined. Within the MEEP project, we're looking at very long vector lengths where I can actually have an application vector length. It can be translated into a virtual vector length, and then a physical vector length that's implemented in the hardware in the Acme accelerator. The notion is Acme knows all those things, and so I don't have to understand from a prediction perspective how big my loop is because I know what the application length is and it's stored in the architecture as an example. So that gives me those capabilities. I have to be able to provide mechanisms through the ISA to transmit that information, right? So that's kind of the big issue there, and then understand what that is. So if I put this all together, I have an architecture which is built for specific big rock movement things. These are big libraries like BLAS, FFT, right? In the HPC space, you pick your top 10. Those will be fundamental building blocks to everything. If I can do that co-design process for that efficiency layer, I get big wins there. One of the big applications that we run in BSC is GROMACS. So if I optimize GROMACS for my RISC-V accelerator, I'm gonna get big wins because GROMACS is used not only for normal stuff, but also for some medical applications that I showed, like the BioBB uses GROMACS as an underlying component. So that's another way that I can get more uptake of the efficiency in doing the co-design because I've built out the building blocks as opposed to doing a very small sliver. And that's the approach we're doing. So in the European pilot project, we're actually doing optimization of GROMACS for RISC-V for a vector processor, right? So that gives me that part of the stack. We're doing it for particular BLAS libraries, BLIS, and runtimes. So again, trying to move those big rocks to get us coverage at the hardware-software co-design. So that's kind of one way to do it. Separation of the efficiency layer at the bottom from the productivity layer at the top, and then picking and choosing the biggest elements to move first, and then get traction because you demonstrate that. And then people will come if you can say, hey, I get good performance by doing the optimization. If we can't show that, then there's no point. So I think, does that answer your first question? Yeah. All right, the second question was about hardware.
The complexity that power efficiency can bring to the equation.
Thank you for the reminder. So complexity aspects. We have moved away from performance as the metric, right? And from a functional perspective, when I talked about the exascale thing, basically that boils down to, at 20 megawatts for an exaflop, I need to have 50 gigaflops per watt. That's an energy efficiency metric. That's the density issue that I have there because of energy density, volume, all those things. So we've already moved to a space where energy efficiency is critical, and we're seeing that being a driving force for a lot of research moving forward and for a bunch of things that we're doing. So it's not only, you know, we're limited in frequency and frequency capabilities, so now we have to look at where we get the most energy efficient components. And a lot of times in this, I don't have this curve in the slide deck, but you'll see, okay, I have a voltage range which I can run the processor over. What I end up doing, instead of maximizing for the frequency, I'll bring the performance down and reduce the voltage so I get closer to the threshold voltage, which gives me the optimal energy efficiency point. And it's, you know, one of those things where I'm trying to then manage leakage power versus runtime power, and so that's the interesting thing. So that's really a driving force for what we're doing in the design. I have a couple projects where in proposal phase to drive energy efficiency, performance per watt. There are also other non-functional parameters that are important. Security, right? If I'm building a bunch of devices, or in the HPC context, how do I provide security? So that non-functional metric is becoming important, and that can be root of trust, secure boot, all these things, crypto, a bunch of interesting things there. So we're seeing not performance as megahertz or gigahertz, but energy efficiency and then non-functional things coming on board. Reliability is also a big problem. You know, as I build these systems, one of the crazy things in the cloud, if I have 2,000 machines, I'm guaranteed at least one failure in like 2 hours or something crazy like that, right? The same thing applies in HPC because it's the same building blocks. How do I mitigate that? And it's either a software, hardware, or both solution.
Thank you. Any other question? Sure.
Hi again. The talk, the aspects you mentioned during your talk. So most of these RISC-V processors are built to optimize the GROMACs, machine learning platforms, etc. But I was checking that, for instance, RISC-V is also being used by some storage vendors. Seagate is incorporating this. I believe this probably is being incorporated as storage controllers or something like that. Mm-hmm. So in the beginning of your talk, you mentioned that one of the problems of these new type of applications, TensorFlow, etc., they are data-centric, they will handle a lot of data, they will store a lot of data, access a lot of data with some random patterns and some things that, for instance, can saturate the parallel file system, etc. So we can optimize, of course, the file system, the software there. But in these projects, or are you aware how RISC-V is being applied to the storage components, SSDs, disks, etc.? And if it can help there, is there some research on this part?
So there's always research on all aspects. Let me start there. And maybe I wasn't clear in the motivation, but RISC-V is starting in the embedded side. So your hard drive or SSD controller, that's where RISC-V is. It's being used in a bunch of low-end places where I don't have to pay a license fee to use a core, and I just need a core to do those with a reasonable rudimentary tool chain, right? So the 1 billion plus cores that have been delivered by RISC-V so far have all been in the embedded side. And so much like we were talking about with Mont Blanc and this notion of using a CPU from a cell phone, we're saying there's the capability to use this embedded core, this thing where it's gotten traction at the high end. So fundamentally, we have a lot of traction from the low end in the context of embedded IoT for RISC-V, and we're saying we can also drop it into the high end and then grow those together. And so the challenge that we have is making sure that it has capabilities associated with HPC from a hardware perspective. So larger address space support, things fundamental to high performance computing from a hardware perspective. That's really what we're driving for at that level, and then the software will come with it. And so it's really one of those things where we have this exciting space where high performance computing and open source software have come together, and those are moving in a positive direction. Because we have open access to the software, we now can build hardware that can leverage that open source software and bring those two things together. To be very crystal clear, right, accelerators are an easy first target because I minimize the software surface area. If I was building a general purpose processor today, I probably, for HPC specifically, let me be very specific, I probably wouldn't build it with RISC-V. I need probably another 5 years for the software ecosystem to catch up such that I can support RISC-V in a general purpose context. So there's a whole bunch of things that are going on, but as you see, we're trying to do the compilation piece, the software piece, what big rocks we need to move, all those things to drive an ecosystem that's ready for RISC-V as it matures and kind of co-develop them together. Does that make sense?
Yeah, thank you.
Sure.
I don't think we have more questions, just checking there, no? Okay, so John, thank you very much once again. That was really inspiring, and historical lesson. Okay, so and hopefully we'll do something together with BSC and in terms of
that would be great.
The LOCA project. Okay, thank you
Fantastic.
very much.
Thank you, everyone.
Thank you for your questions and interesting insights. We will wrap up our annual conference with Rui Oliveira.
That's it. That's the end of conference. From what I saw, most of the events of the conference, bar the parallel masterclass, and I think they were all really interesting to follow. We always learn something, and coming to different areas of knowledge. It's always refreshing, and that's the spirit of the international partnerships and connecting the dots. So thank you all very much again. Thank you all my team that put together the conference, which is, as you might know these days, it's much more difficult to do in an hybrid environment. Thank you all again, and see you next year. Okay, thank you.